In this section, we will look at flow and loading patterns as well as other input dynamics and think a little bit about how we account for these, if at all, when we're doing our modeling projects. So we will discuss flow and loading patterns, where we change the pattern based on daily averages. That is to say, where we're varying the influent flows and concentrations of COD, TKM, total phosphorus on a day-to-day basis. And then we will compare and contrast that with simulations where the patterns are defined based on hourly averages. That is to say, where we're varying flows and concentrations from hour to hour. So we'll look at two different time resolutions and how that impacts our simulation results. We'll look at how we work with real and synthetic data sets. And then finally, we'll also look at other inputs that we might want to be accounting for dynamically, such as trucked septage. So trucks that are coming into the site carrying septage from septic tanks. Side stream loads. If we're doing dewatering of digested sludge on site, then the reject water represents a side stream load that we might want to be accounting for dynamically, as well as maintenance events. So for example, when a bioreactor train is taken offline because we want to do maintenance or we want to clean the aeration diffusers, a very common event that we might want to be accounting for in our simulation dynamics. Okay, if you recall, in one of the previous presentations, we looked at a case study in which we simulated a 3-pass activated sludge process, and our goal was to calibrate the model to the reported sludge production, mixed liquor suspended solids concentration, and airflow requirements for that plant. And we did a pretty good job. After iterating a few times around modifications to the influent wastewater fractions, so the fractions of the COD, and adjusting the SRT to better reflect what they thought they were operating their plant at, we were able to get within 10% of the reported mixed liquor suspended solids concentration. So the model that we used was within 10% prediction of the mixed liquor suspended solids concentration, within 10%, or maybe it was 11% of the reported sludge production in the waste activated sludge stream. And then we input directly the airflow, the reported airflow, into the bioreactor using an assumed diffuser density taper. And we were able to simulate a DO profile that showed about 2 milligrams per liter of oxygen in the second and third pass, and then around 1 or less than 1 milligram per liter in the first pass, which seemed to be more or less representative of what we might expect to see in a full-scale system where they are instrumenting and measuring DO in the third pass. When we looked at the predicted effluent quality of this 3-pass system, operated an SRT of 8 days and 20 degrees Celsius, we found that the model predicted an effluent ammonia concentration of 0.11 milligrams nitrogen per liter. So the question we ask ourselves now is, would these results change if, instead of simulating under steady state conditions, using a constant influent, a constant flow and load coming into the process, what would be the result if we simulated the model dynamically with an influent that was varying, where the flows and loads were varying? And so that's what we're going to look at now. First of all, we need to develop data sets that we can import into the model to capture that variability. And so what you see here is a table in which we've set up for about a year, on a day-to-day basis, the different values of the flow, so Q, and the concentration of COD, TKN, and TP. So we can import these values into the model, and then additionally I've calculated here the COD as a load, so kilograms per day is simply column C multiplied by column B. So you can see here over the course of about a year the variation in the flow in the influent flow, the COD concentration, the TKN, and the phosphorus. And you can see what the variability sort of looks like. At the beginning of the year, we have maybe these are some storm events, or maybe a rainier season in which we're getting more inflow into the system from runoff or from infiltration into the sewer network. And then towards the end of the year, we have lower flows coming in, although some spikes likely due to rainflow events. And so we're going to import this data into the model. In addition, we also have variability related to temperature. So we can see here the temperature varying from 15 degrees Celsius up to 25 degrees Celsius. So we want to capture that in the model. And then also over here, this parameter that's labeled FR-SNHX, TKN. And this represents the fraction of the TKN in the influent that's ammonia. So at any given time, you can see throughout the year that this fraction varies from about 50% up to 75%. Temperature data is important because our biokinetic rates are all dependent on temperature. So typically, our biokinetic rates are higher when the temperature is higher and lower when the temperature is lower. So we want to capture that. And usually temperature data is readily available because most instruments will have temperature sensors on them, and that data is typically logged. So that's usually accessible, and we can get that and import that into the model. As for this fraction FR-SNHX, TKN, it indicates that they must be measuring ammonia and TKN in the influent, and capturing the variability in this fraction could be important to us because it will improve the accuracy of our simulation of nitrification dynamics. Okay, so in a following presentation, we're going to look at how we do this hands-on, but for now I'm just going to show you the results. And so we think about importing all of those dynamics, not just the flow, but also the COD, the TKN, the phosphorus, the temperature, and the ammonia fraction into the influent of our model here. And so that data would be imported into this influent element, and then when we simulate the model dynamically, then we would generate an output on a dynamic basis. And you can see some very interesting things here, that for the most of the time, our effluent ammonia is well below 1 milligram per liter, probably pretty close to that 0.11 milligram per liter of ammonia in the effluent that we were predicting under steady state conditions. But a few times a year, maybe 4 or 5 times, we can see that the effluent ammonia concentration being simulated by the model spikes. It's much higher than 1 milligram per liter. We're reaching 5, even 10 or 12 milligrams per liter. So what we conclude is that whereas the steady state simulations indicate an effluent concentration of less than 1 milligram nitrogen per liter, dynamic simulations tell a somewhat different story. Sometimes it's less than 1 milligram per liter, but sometimes it's significantly higher. Sometimes we don't just want to look at time variability on a day-to-day basis, but we also want to look at it on an hourly basis. But the data, particularly influent concentration data, may not be available at this time resolution. Most plants may be sampling the influent and measuring COD, TKN, TP, or BOD, TSS, and VSS. They may be doing it every day, but most plants don't do that every hour. So if we want to simulate that variability on an hour-to-hour basis, we're going to have to generate a synthetic data set. And we're going to do that assuming a sinusoidal influent pattern. So we're just going to use a math function and apply that to our data set to generate hourly or diurnal time variability. This is not necessarily the best practice for how we generate a synthetic data set. Best is probably to get a representative diurnal profile from a sampling campaign at the site or from a nearby plant if they've done this before. However, it is simple and it will illustrate some good things for the purposes of this presentation. We will normalize the amplitude of the sinusoidal curves using peaking factors, and this is an important term to have as part of our jargon or our nomenclature, is the notion of peaking factors. And they will be applied to flows and loads, not concentrations. That's also important to know, that we're trying to maintain continuity of average flows and loads between steady state conditions when we simulate dynamic daily dynamic data, or when we simulate hourly dynamic data. We want continuity of the average flows and loads, but not necessarily the concentrations. So we're going to use a sinusoidal function. And so the sinusoidal function is what was used to generate these two tables here, and what is plotted in these blue and orange curves. The function is as simple as this. So the factor at any given hour of the day is equal to the sine function of the time, or the hour of the day, if you will, divided by 24 times 2 times pi, multiplied by an amplitude, and then added to a bias. And so in this case, the amplitude is really the peaking factor we're looking for. So if we want a peaking factor of 1.3, then we set an amplitude of 0.3, and then we apply a bias of 1 so that the average of that curve will be 1. So we have two tables here, one for the loading profile and one for the flow profile. And you'll note that the peak on the load profile is somewhat higher than that for the flow profile. And that's very typical of municipal sewage, that the variability in the load tends to be somewhat higher than the variability in the flow. So we're using a peaking factor of 1.3 for the flow and a peaking factor of 1.5 for the load. All right, so with that, we are able to take this data on the left-hand side, in which we have daily varying flows, and if we run an algorithm through those daily flows, we can interpolate for every hour an average hour flow. And so you can see here the resolution of that data is a little higher. And we apply that not just to the flows, but we apply that also to the loads of COD, TKN, and total phosphorus. And so that's a little exercise that we can automate. You can certainly do it manually, or you can automate it using a Visual Basic or a VBA script or a Python script. There are different approaches for doing that. So here you can see we have developed now the diurnally varying or hour-to-hour variation patterns of flow, COD, TKN, and TP. And what's important to do is just to do this exercise in which we go back and verify whether our hourly loading patterns now, whether they still provide the same averages as the original data set on which they were based. And so you can see here, for example, in the flows, when we plot the daily averages for some 7-day period, so this is from day 100 to day 107, you can see that the daily average flows were varying ever so slightly, trending downwards. And you can see that the interpolated hourly averages based on our sinusoidal loading pattern, you can see that they're oscillating around those averages very nicely. And when we calculate the average for the entire data set, for the daily pattern and the hourly pattern, we get the same average. So there's no loss of information. The average flow coming through the plant whether we are assuming steady state conditions or whether we're assuming the daily pattern or whether we're assuming the hourly pattern, is the same 11,850 meters cubed per day. Similarly, down here, when we look at the COD, loading in kilograms per day, we can see the variability in this one for the daily pattern. So that was based on actual measured data or reported data from the plant. And we can see how that one varies. And then we can see in the orange plot how our interpolated synthetic data set based on the sinusoidal loading pattern, how that one varies around the daily averages. And so that visually looks to make sense, but we need to do another step in which we actually calculate the averages for the entire data set, not just the day 100 to 107 period, but for the entire data set. And we see that indeed our daily pattern has an average loading of 4,913 kilograms per day, which matches exactly our hourly pattern average of 4,913 kilograms per day. So no loss of information here. In contrast, when we look up here at this top right chart, we can see the loading pattern around the COD concentration. We can see that the orange line, so the hourly average, still oscillate nicely around the blue daily average concentration pattern. But when we calculate the averages for these two data sets, the daily pattern has an average COD concentration of 421 milligrams per liter, whereas the hourly pattern has a concentration of only 408 milligrams per liter. And this is to be expected because our loading is highest when our flows are highest. And so our concentrations are skewed as a result of that. So we don't expect to see continuity around concentration, but we do based on flow and loading. And that's a very important point to remember when we're developing the synthetic data sets. Okay, so if we simulate now in our plant, if we simulate the influent loading pattern, not just based on daily averages, but we look at hourly averages, now we can see on the right-hand side the effluent concentration that we simulate, we get a lot more frequent peaks in the effluent. And so this sort of answers the question in terms of, what's the effect of increasing the time resolution around the influent dynamics. We can see on a daily basis, we can simulate about 4 or 5 ammonia breakthroughs in the course of a year. But when we simulate the change in influent loading on an hourly basis, we simulate those breakthrough in peaks a lot more frequently. So the higher the resolution, typically the greater the number of peaks. So do we need to account for dynamics? And at what time resolution? Should we look at it on a daily basis, on an hourly basis, or even minute to minute? Well, typically, hourly data is the finest resolution we will investigate because bioreactor HRT is in hours. And so variability in the influent based on a minute-to-minute basis will typically be buffered out in the bioreactor based on its HRT. But then should we be looking on a day-to-day basis, the variability, or an hour-to-hour basis? How important is it to capture those extra breakthrough peaks in the effluent that we saw on the hourly basis compared to on the daily basis? Well, this all depends on our modeling objectives. We need to ask ourselves questions. For example, are we trying to simulate compliance in the effluent based on ammonia on a 50th percentile basis or a 95th percentile basis? If on a 50th percentile basis, maybe the steady state results are the most important ones. But if it's on a 95th percentile basis, that is to say we need to demonstrate compliance more than 95% of the time or 95% of the days in a year, In that case, maybe we need to be simulating the input dynamics on an hour-to-hour basis because we want to see all of those breakthrough peaks that we're expecting. Now let's talk about some of the other inputs we should consider when we're running dynamic simulations. We looked at flows and loads, and we saw how varying the flow and load on a daily basis or even an hourly basis had impacts on the simulated effluent ammonia concentration. We even looked at how we could vary the influent wastewater fractions, notably the fraction of the influent TKN comprised of ammonia, and we could vary that on a daily basis. We looked at time variation of temperature over the course of a year between 15 and 25 degrees Celsius. But what are some of the other inputs? Well, we can talk about trucked septage. Many activated sludge plants provide treatment for trucked septage that's brought in from outlying rural areas where they don't have their own treatment infrastructure, or other mobile sites like construction sites. The same is true for many industrial wastes, for example food wastes or other industrial wastes that might be being trucked into the site and discharged into the liquids treatment stream. These are inputs we should think about. In addition, side stream loads. Whereas at some plants, they will operate their sludge dewatering 24 hours a day and 7 days a week. And so if we're thinking about the reject water from anaerobically digested sludge that's being dewatered, that load being returned into the activated sludge process under those conditions can be treated as a constant load and simulated even under steady state conditions. However, many plants don't operate 24/7. They might only operate 1 day a week. And during that day, they may only operate 8 hours a day because the operator is only on site 1 day a week and he wants to go home at the end of the day. Under these conditions, maybe we need to think about simulating these reject waters from sludge dewatering in a dynamic fashion to account for that slug effect of bringing in the entire load in an 8-hour period 1 day a week. Overall, I'd like to conclude by trying to answer the question, when can inputs be treated as averages and when do they need to be simulated dynamically, and simply say that it really depends on the modeling objectives. And it's incumbent on us, you and I, the modelers, to bring the insight necessary to understand the objectives of our modeling project and how they influence decisions about how to account for these dynamics. Now in a next step, we will look at how we implement dynamic inputs in a hands-on exercise. So I hope to see you there.